Okay, so let's continue. I make a few changes to the circuit, okay, from previous, just for the sake of showing you how the conversion works. Now, if you look at my circuit now, I've connected directly the DC generator directly to input 0. Okay, so for purposes of showing you the conversion, I disconnected the input to the variable resistor. So let's say, okay, we know that using the table here, that one step or one resolution bit is equals to 19.6 millivolt. So if we round that number up, it should be 19.6. If I round it up, it should be around 20 millivolt per step. Okay, it should be around 20 millivolt per step. So, okay, 20 millivolt per step. So let's say I adjust my input to 20 millivolt. Voltage 20 millivolt. Okay, so by theory, we only have one bit on. So we only have one step. So if I simulate here, you see, we only have one bit simulated here. So let's say I change it back to 40 millivolt. By these changes, I should have only bit that represent the value of 2 steps is going to high. So if I make, you see, so it's no longer this bit, but it's the second bit that is going high. Second bits mean this is a 2-bit resolution. So that means we are using 2 bit to represent 2 millivolt. Okay, so let's say I change it to something much more. Let's say I'm changing it to 100 millivolt. 100 millivolt means that it should be represented by 5 bit. 5 bit. If 5 bit means I should have this one. The bit 0 is high. Bit 2, bit 1 is 0, and bit 2 is high. So it should be 1, 0, 1. Okay, so let's try it. Yeah, so you see, this is how the digital, the ADC converts an analog to digital. When it receives a value by using a time discrete, you see that the clocking here. Every time it clocks, it will start the conversion, and whatever value inside in 0 is going to be converted into digital. So let's have let's reverse engineer a little bit. Okay, let's say, okay, let's change it back. So let's say I connect it back here, and this is connected here. Okay. Okay. So now the connection should change. So if you see 0 volt, if I change it, okay, so 2 is still 1 bit. I increase the value, it's slowly rising up. You see, when the value of the voltage is increasing, slowly the binary bits are counting up, following the increase of the voltage. You see? Okay. So let's say, oh sorry, I think I've changed it too much. Okay. I think I messed up something here. So let's say I stop it first. Okay. Okay, so let's say let's say I change the value of the variable resistor here. Okay, let's say I change the value here to the maximum 5V gain, and then here is connected directly here parallelly. So here, if you look, it says it's 3.62 volt. So let's convert 3.62 volt. Let's say I'm using my calculator. Okay. So using my calculator, I'm going to calculate 3.62 volt. 3.62 volt is in the value. If we have 3.62, if we know that, let's change it to a normal calculator. 3.62. Oh, sorry. 3.62. Okay. This is the normal volt here. Oh, so let me change that. We know that 1 bit is equals to 20 millivolt, or actually it's 19.6 millivolt, or equals to 0. Millivolt, 0.019 6 millivolt. Okay, so if we want to know what's the bit representing 362, this is divided by 3.62. We are going to have oh, wait a minute. Oh, sorry. I got it all wrong. I should have used a digital calculator. Let me calculate on my calculator here. If we have 3.62 divided by 3.62 divided by 19.6 milli. I got the value here is actually 184.6. So I'm going to round out the number to 185. 185. So again, I'm going to call my calculator. 185. I'm going to use a programmer calculator. So it says that the decimal value is 185. So if you look, 185 is 185 is 101111001. So this is 10. Oh, sorry, I'm reading it invertly. So MSB LSB 1011 1001. So 1011 1001. You see, so this shows that the conversion is happening, and it's happening following just a basic rules of 3.62 divided by 19.6 millivolt. So 3.62 volt divided by 19.6 millivolt, I get 185. So 185 in decimal, change to binary, I got 1011 1001 1011 1001, the same number here. So this shows that the conversion are happening correctly. Let's say now I'm going to use the VREF option. Okay, so it says here, if I want to to measure the input of 0 to 4 volt, I need to give the reference VREF positive VREF 2 volt. Then I can adjust the input. So to get from 0 to 4 volt in a step resolution size of 15.69. So to do so, I need to change the VREF. We have two VREF here, VREF positive and negative. I need to change the VREF of positive. So let's say I'm disconnecting it here. I'm using a DC generator. I'm going to generate 2 volts. Okay, so judging from the 2 volts here, so I'm going to adjust this one to just 4 volt. 4 volt. Okay, so this is going to be okay. So let's try the simulation again. 4 volt is maximum. Okay. Okay, so let's say we have changed. Okay, this is it. The value is 0.4 millivolt. Let me just use, because it's not that accurate. Let me disable this wire and disable this. So just directly connect this here. Okay, so here, because it's full, let's say I'm giving it 1 volt. Okay, so this is the value for 1 volt. If you look at the table given, so for now, if I'm giving VREF 2 volt, I can measure from 0 to 4. So I'm giving now 1 volt. It has 1 volt with a step of 15.7 millivolt. So calculating 15.7 millivolt, right now 1 volt. So let's change it. 1 divided by 15.7 shift milli is equals to 1 divided by 15 is equals to 63.6. 63.6. Okay, using the calculator method earlier. That means here I am using calculator. 1 volt divided by 15.7. So let's say divided by 16 is equals to, oh sorry, I need to change to standard calculator first. So 1 divided by 15.7 is equals to 0.636. So it's closer to 64 if you minus the milli. So change it to the programmer again. So 64 in decimal, 64 is equals to 63. Change it to 63. So 63 is 0. Okay, so if you look at 1, 1, 1, 1, we have 4, 5, 6, 6, 1. 1, 2, 3, 4, 5, 6, 7, 1. Okay. Hey, wait. Why? I think I've done something wrong here. Let me check. Okay. So let me get back to you on that one. First of all, you can go through the exercise. Try changing the value of VREF, positive and negative side, and see what's your limit of conversion is. Okay, I'm going to stop this part right here. Okay, so we will discuss in our later on video on about ADC and how to use it on to our microcontroller. So don't forget, check your VLE for the codes and for the schematic diagram. Okay.